Why is the sky blue? It sounds like the simplest question in the world, one we ask as children. You're probably thinking, it's the reflection of the ocean. And what if I told you that that's one of the most popular and persistent scientific myths out there? The truth has nothing to do with the sea. It's a far more epic story, involving the sun's light, Earth's atmosphere, and a bizarre physics phenomenon that explains not only the color of the sky. Prepare yourself, because today we're going to unravel one of the most fundamental mysteries of our existence. And I guarantee the answer is stranger and more fascinating than you ever imagined. To understand the secret of the blue sky, we first need to understand our protagonist. Sunlight. The light we see as white or yellowish is actually a disguise. It's a composite of all the colors of the rainbow, each traveling as a wave. Think of it like a team of runners. Red light has long, lazy waves, like a marathoner with a wide stride. Blue and violet light, on the other hand, have short, energetic waves, like a sprinter taking quick. When this team of colors travels through the vacuum of space, they stay together, and the light appears white. But everything changes the moment they hit our planet's protective shield, the atmosphere. It's an invisible soup of tiny gas molecules, mostly nitrogen and oxygen. These molecules are incredibly small, even smaller than the wavelengths of visible light. And this is where the magic, or rather, the physics happen. When sunlight hits this molecular soup, a phenomenon called Rayleigh scattering occurs. Imagine throwing a marble into a field full of tiny pebbles. The marble will hit the pebbles and bounce off in all directions. But not all colors bounce the same way. Remember our runners. Red light, with its long, lazy waves, is like a big, heavy truck. It can power right past most of the tiny gas molecules without being disturbed much. It continues its path, almost in a straight line towards our eyes. But blue light, with its short, energetic waves, is like a tiny pinball. It's the perfect size to collide violently with the gas molecules. When a wave of blue light hits a nitrogen or oxygen molecule, it gets absorbed and then re-emitted. It gets scattered and scattered and rescattered all across the sky. So, when you look up on a clear day, what you're seeing isn't sunlight coming directly to you. You are seeing the blue light that has been scattered by trillions upon trillions of gas molecules. This blue light bounces all around the atmosphere and reaches your eyes from every direction. That's why the entire sky appears to glow with the color blue. It's not a reflection. It's not a color inherent in the air. It's a planet-scale optical illusion created by the frantic dance of blue light. But this leads to an even more intriguing question. If violet light has an even shorter wavelength than blue, and therefore scatters even more efficiently, why isn't our sky violet? The answer is a combination of two factors. First, the sun emits less violet light than it does blue light. The sun's team of colors isn't perfectly balanced. Second, and more importantly, our eyes are less sensitive to the color violet. Evolution has shaped our eyes to be most sensitive to blue, green, and red. So, while there is a lot of violet light being scattered up there, our eyes simply don't register it as well. What we perceive as sky blue is actually a mix of all the scattered blue with a little bit of green and violet. the perfect combination for the receptors in our eyes. And what happens to the rest of the colors? The red, orange. As I said, most of them pass straight through the atmosphere without being scattered much. That's why, when we look directly at the sun, it appears white. But we're seeing the mix of all the colors that didn't get scattered away. But this same physics explains one of nature's most beautiful spectacles: the sunset. When the sun is low on the horizon, at dawn or dusk, its light has to travel through a much thicker slice of the atmosphere to reach our eyes. It's like the race just got much longer, and with many more obstacles. On this extended journey, almost all of the blue and green light is scattered away. They get filtered out. The only colors that survive this long and difficult trip are the long wavelength ones. The reds, they are the ones that finally reach our eyes, painting the sky with those spectacular warm colors. The same sky that was blue during the day now reveals its most resilient colors. A red sunset isn't the end of the day. It's a celebration of the light that survived the longest journey. And on other planets, the sky isn't universally blue. On Mars, the atmosphere is very thin and full of reddish dust. There, the daytime sky is a butterscotch. But, fascinatingly, the sunsets on Mars are blue. This is because the Martian dust scatters the red light away, allowing the blue light to come more directly to the eye. When the sun is on the horizon, the exact opposite of what happens on Earth. The next time you look up at that vast blue ocean above your head, remember the incredible journey that light took to reach you. Remember the invisible battle between photons of light and molecules of gas. Remember that you're not seeing a color, but a planet-scale optical illusion. A phenomenon that tells us the story of our atmospheres, composition, and our own eyes. Sensitivity. The blue sky isn't just a backdrop to our lives. It's a constant reminder of the complex beauty and elegant physics that govern our universe. What other mystery of science or nature have you always wanted to unravel? Leave your question in the comments, as it might become the topic of our next video. And if you enjoyed learning the truth behind one of humanity's most fundamental questions, don't forget to like this video, subscribe to the channel, and hit the notification bell so you don't miss any of our next journeys.